So for number 70, they tell us that an is convergent. And then it says that show that the limit as n approaches infinity of an plus 1 is equal to the limit as n approaches infinity of an. So let's begin with the information that they give us that an is convergent. And now remember that a sequence is convergent if it has a limit, right? So as n gets larger and larger, it tends to a specific limit. So we say that an is convergent if and only if, so if and only if, the limit as n approaches infinity of an is equal to some limit L, right? If that limit exists. Okay, so now that we have established that this limit exists, let's think about what does it mean for the limit to exist? What is it telling us? So for the limit to exist, it means that you can get, and I'm going to maybe put a little n in here, and this is the value of the sequence, right? So when this limit exists, it means that the value of the sequence, so this would be here, would be an, the value of the sequence is always within some kind of tolerance, right? And we call this the epsilon neighborhood. It means that if you go from the limit, you can either go up by a little epsilon here or down by a little epsilon. But your sequence will always, the value will always be inside this little tolerance. And the reason that this matters is because we're saying, hey, what if I want my the value of the sequence to be, I don't know, 0.1 from the true limit, right? So what we mean by this is saying, okay, an, the value of the n, minus the limit, so the distance from the actual value that it outputs to the limit. So for example, if I were, let me erase this. If I were at this point here, right? And we can see that the limit is slightly above. So we can say that the distance from my an to the limit is definitely less than some epsilon, right? And I could say, hey, I want that distance to be 0.1. I want it to be 2. I don't know. You're the one who decides the kind of distance that you want. And the caveat here is that epsilon has to be greater than 0, right? Negative distance, in this case, it doesn't really make sense. So we're saying, hey, if the distance between the actual value of my sequence and the limit is less than some epsilon, this happens whenever I choose, I evaluate my an at a little n greater than capital N. Now, this may sound a little bit mathy, if you will, but it just means that beyond a certain point, so that certain point would be my capital N here, beyond this point, if I choose any n, right, so maybe I choose here, we can see that the output of my sequence, which is going to be this point, is definitely going to be within the epsilon neighborhood, right? Whereas if I choose an n before my capital N, so if I choose it here, if I choose this one over here, we can see that my an is going to be outside the epsilon neighborhood, right? So what we have here is just saying, hey, if you choose a value that is beyond this point here, then the value of your sequence is definitely going to be within the epsilon neighborhood. Okay, so that's what it means for the limit to exist. Okay, cool. So this, we've established that an, the limit exists, and if it exists, it means that it follows here this definition, right? And I should put for epsilon greater than 0. Okay, so let's see then what happens to if I choose not n, suppose this is my little n, right? But I choose n plus 1. I choose n plus 1 here. Well, we can see that n plus 1 is definitely greater than n, right? And n, because the limit exists, is definitely greater than capital N. So we have here that n plus 1 is going to be greater than capital N. And so because this is the case, then we can say, okay, a an plus 1 minus L is less than epsilon, right? And this is true because an, so this is an here, this point, it was within the epsilon neighborhood. So because an plus 1 is beyond an, it also means that its output is also within the epsilon delta neighborhood, right? Or another way to show this would be to actually work backwards. It's to say, okay, an plus 1 minus L is less than epsilon if n plus 1 is greater than n, right? But this means that then that n is greater than n, capital N minus 1, which is true. Because remember that we said that little n was greater than n. So definitely little n is going to be greater than n minus 1. That is going to be true in all cases. And so we have shown here that if the limit of an is L, then the limit of an plus 1 is also going to be L, because it also lies within that, that epsilon delta neighborhood, right? And so that is it for our item A. We have shown this. So now let's deal with item B. So for item B, what do we have here? We have that an plus 1 is going to be equal to 1 over 1 plus an, right? And that a1 is equal to 1. And then assume that an is convergent, then find its limit. Well, if an is convergent, then the limit as n approaches infinity of an is equal to some limit L, right? But as we've shown previously in A, if the limit of an is L, so is the limit of an plus 1, right? Because we've shown that in item A. So actually, this limit here is going to be, the limit of an plus 1 is going to be L is equal to 1 over 1 plus, the limit of an is also L, right? And so if we multiply this, we're going to get that L times 1 plus L is going to be equal to 1. And then that means that we have, I'm going to distribute this, so we have that L squared plus L, and then I'm going to bring this 1 to the other side, minus 1 is equal to 0. So here we have to figure out the values for L, right? And this is just a quadratic, so we're going to use the quadratic formula. Minus b plus or minus square root of b squared minus 4ac divided by 2a. And in this case, we have that a is equal to this coefficient here, which is 1. A is equal to 1. B is going to be equal to also positive 1. And C is going to be equal to negative 1, right? Oops, I should have written this. Negative 1. Okay. And so if C is equal to negative 1, now we plug into this formula. So minus B, so minus 1, plus or minus square root of 1 squared, so 1, and then minus 4ac. So minus 4 times 1 times negative 1, and all of this divided by 2. And so this is going to be equal to, let's see, minus 1 plus or minus square root of 1 minus 4 times 1. 4 times 1 times negative 1, it's going to be minus 4. So 1 minus minus 4 is equal to root 5 divided by 2. And so our values for L is either 1 plus root 5 divided by 2 or 1 minus root 5 divided by 2. But our limit can't be negative. So here what we have is that we're just going to consider the positive root. Yeah. And so L is going to be that is minus 1 plus square root of 5 divided by 2, and that is what we get for item B.